Hello everyone, and welcome to this lecture on the second part on number theory. Last time we were talking mainly, the main focus was about modulo arithmetics, so the arithmetics mod P, and we studied the properties of such arithmetics and how it works, and we can write equations, we call them congruences in that system, and some of the properties of that system, which makes it very similar to the regular integer system. Now we are going to discuss also another important pillar of the number theory, which is the prime numbers, theorems related to prime numbers, and some properties of prime numbers, and the problem of testing from primality, as well as a couple of important theorems, the Chinese remainder theorem and the discrete logarithms. Remember last time we already mentioned that what is a prime number? Prime number is a number that cannot be written as a product of other numbers, which means that it's a number that cannot be factored out, which means that it's a number that does not have any other divisors except itself and 1. So it can only be divided by 1 and divided by itself. Cannot be divided by any other integer. And then there is an important theorem that we mentioned also last time, which is, we mentioned that it is a key theorem in number theory, which says that for any integer which is greater than 1, that integer can be factored out. And factored out here means that it can be written as the product of prime numbers. Each one of them is raised to an integer power. Now, what are the values of those prime numbers? How many we have? What are the powers for each one of them? The theorem does not talk about that. It only says that any integer number which is greater than 1 can be written as the multiplication of its prime factors. Each one of them is raised to a certain integer power. Okay, and this is called the fundamental theorem of arithmetic. It's something that you have been using since your maybe late years of your primary school, where you were factoring out numbers to their prime factors, right? So that's something which is well known. Now, this table is meant to show you how the prime numbers look like in the range from 0 to 2000. One big issue of the number theory is actually figuring out the prime numbers in a particular range. There is no general formula that tells you what are the prime numbers in a particular range. The only way to figure that out is to go through the numbers one by one and then test them for what they call primality. So you test whether a particular number is a prime number or not, right? And this just shows you what are the prime numbers from the range from 1 up to 2000. Okay, so first and most important theorem in number theory that has to do with the prime numbers is the Fermat's theorem. And the Fermat's theorem says that if you choose a prime number p, and then you choose any positive integer a, which is not divisible by p, so p is not a factor of a. Okay. Then in this case, if you take that integer a and you raise it to the power p minus 1, the result is going to be equal to 1 mod p. So the result that a to the power p minus 1, where p is a prime, is always going to be equal to 1 mod p under the condition that a is not divisible by p. So p is not a factor among the prime factors of a. Right? Now again, you can rewrite the same exact formula by just multiplying both sides of this congruence or equation by a. So if you multiply here a, it becomes a to the power p instead of a to the power p minus 1. And if you multiply here by a, it becomes a instead of 1, right? And we know that from the properties of modulo arithmetics and congruences, that if you have a congruence or an equation and you multiply both sides by a constant, it stays as an equation. The equality stays, right? We know that from the properties that we looked at earlier. Now, how is this useful? And by the way, not only this, but the coming few theorems, such theorems allows you to do calculations of very large numbers in modulo arithmetics. And let's take the example of, if I ask you, for example, what is the, let's say you get a question that says, what is the number one, calculate the following: 1, 4, 0, 4, 8, 5, 7, 6, for example. Okay, so, okay, and you want to calculate this mod 3. So the question says, how can you calculate this mod 3, right? Now, doing it right now, I mean, imagine you need to divide this whole thing over 3 and you continue with the regular long division until you get the result and the remainder. But that's really computationally very expensive. However, we can notice that this number is actually 1024 squared, which is actually 2 to the power, so 1024 is 2 to the power 10, so that's 2 to the power 20, right? Now, if I want to calculate 2 to the power 20 mod 3, now here I have a number, consider this as A. I have a prime, consider this P. I notice that P does not divide A, so is not a factor of A. That's exactly what's required here in Fermat's theorem. So accordingly, I know that 2 to the power 3, right, mod 3 is definitely equal to 1, right? So 2 to the power P is equal to 1 mod P using Fermat's. That's from Fermat's. How is this useful in my case? Well, I have here 2 to the power 20, which can be written as 2 to the power 3 raised to the power 6. That's 2 to the power 18, right? Multiplied by, so that's, yeah, 2 to the power 3 to the power 6, that's 2 to the power 18. And I have 2 to the power 20. So this is multiplied by 2 to the power 2, right? Right? That's how can I write this number, right? Now, I notice that if I want to calculate all of this mod 3, I notice that 2 to the power 3 mod 3 is equal to 1 from Fermat's theorem, which means that this thing, mod 3, is 1, and then I have 1 raised to the power 6 multiplied by 2 to the power 2, and all of this is mod 3, right? But then 1 raised to the power 6 is 1, so I end up with, the result here is 4, right? 2 to the power 2 is 4 mod 3. But what is 4 mod 3? It's actually 1, right? 4 divided by 3 is equal to 1, and the remainder is 1. So this becomes a 1, correct? So basically, I was able to find this, okay, mod 3, without really having to go through the long process of long division, which would have taken much more number of calculations using Fermat's theorem. So that's basically the usage of Fermat's theorem. And as I mentioned, can be written this way or that way. That's just an example how you can use Fermat's theorem calculations, right? Now there's another theorem which is also as important as the Fermat's theorem, and it's called the Euler's theorem. That theorem does not really deal with the numbers directly, but deals with a mixture of the numbers and a function. And the function is called the Euler's totient function, phi of n. What is the Euler totient function? Phi of n is the number of positive integers less than n and relatively prime to n. Relatively prime to a number means that doesn't have a common divisor, okay, with n except 1. That's the meaning of relatively prime. So there is no common divisor between the two numbers except 1, because of course 1 will divide everyone, right? So for example, if I try to find the phi of 10, so this is the number of positive integers smaller than 10 that are not that do not have any common divisors with 10. Let's list those numbers. So the 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? These are the numbers smaller than 10. 1 is always included. 2 has a common factor with 10, because both of them can be divided by 2. So we cancel the 2. 3 does not have any common factor with 10, so we keep it. 4 is divisible by 2, and 10 is divisible by 2, so we cancel. 4 is not relatively prime with respect to 10. 5 is divisible by 5, and 10 is divisible by 5, so that's not also counted, because it's not a relatively prime number. 6 is divisible by 2, and 10 is divisible by 2, so 2 is a common factor between them, so they are not relatively prime. 7 counts. 8 again is not relatively prime, while 9 counts. So how many? 1, 2, 3, 4. So the phi of 10 is equal to 4. The number of integers smaller than 10 and positive that are relatively prime with respect to 10. Do the same, for example, for the number 9. So let's see, what are the numbers smaller than 9? 1, 2, 3, 4, 5, 6, 7, and 8. Right? Let's see. 1 is always counted. 2 does not have anything common with 9. Count. 3 divisible by 3, and 9 is divisible by 3, so they are not relatively prime. 4 counts. 5, no common factor. 6 does not count. 7 counts. And 8 counts, because both of them, they don't have any common factor with 9. So the result is going to be 1. Going to be 1, 2, 3, 4, 5, 6. Right? So that's 6. Right? And I think the table here shows those two results. For example, the phi of 9 and the phi of 10. And you can try the others if you want to get more understanding of the Euler's totient function. Okay. A question for you. If I want to get the phi of a prime number p, what is this going to be? How many integers smaller than p that does not have any common factor with p, right? Given that the number now that I'm using is a prime number p. I mean, it's quite easy. Let's try, for example, the phi of 7. So what's the phi of 7? Let's see. The numbers smaller than 7 are 1, 2, 3, 4, 5, and 6, right? Is it possible that any one of those numbers will have a common factor with a prime? These are the numbers smaller than the prime. Never. Because they are smaller, so they cannot be multiple, and they cannot have a common factor with a prime, because a prime number is not divisible by anything except itself and 1, right? So this means that all the smaller numbers than the prime will be counted into the phi, into the totient function. So basically, going to be 6 in this case if you count them. And in general, for any prime p, the totient of that p is p minus 1, right? That's just for your knowledge of the totient function. Now, what's the use of the totient function? It's actually used in Euler's theorem. Euler's theorem states that for every a, so if you have two integers a and n, and those two numbers are relatively prime, which means that they don't have any common factor among them. Now we are not dealing with any prime numbers, but relative primality. The two numbers do not have common factors. Then a raised to the power of the totient, the Euler totient function of the other number n, is going to be equal to 1 mod n. And again, if I multiply this side by a and this side by a, I end up with the other form of the Euler's theorem. Again, the Euler's theorem can be used in reductions of calculations similar to Fermat's theorem. Very interesting theorems, right? Now, as I mentioned, one of the key challenges actually in dealing with integers and in number theory, and actually even in cryptography, as we'll see later, is how to figure out a prime number or find the prime numbers in a certain range. There's no formula, there is no fixed distribution. In some ranges you have several prime numbers within a small range of values, and in some other ranges you pass a large number of values before hitting a prime number. So there is nothing fixed so far. Nobody has been able to discover how to find the prime numbers is given a particular formula or in a certain range, right? The only way they do this is that if they want to find a prime number in the range, let's say, of 10 million, then they go to 10 million and they start going through the numbers one by one. So 10 million, 10 million and 1, 10 million and 2, 10 million and 3, and so on. And they go through these numbers exhaustively, one after one, in the desired range, and they test them whether they are prime or not. The testing for primality has been a problem that has been addressed with number theories for a very long time. Until very recently, the most common and most used, and it is still the most used so far, method or algorithm is called the Miller-Rabin Algorithm, which allows you to test for certain properties of the number to see if it's prime or not. And if the number satisfies the properties, then you say it's possibly a prime. You cannot be 100% sure. But if it violates the conditions, then you are sure it's not a prime number. So the algorithm itself is a non-conclusive algorithm. It does not guarantee that if the test is successful, that the number is prime. But when you repeat the algorithm several times, each time on a different factor of the number being tested, and it passes over those several times, you can say that with very high probability the number is prime. Still you can make mistakes, still you can mess the test that allows you to figure out that it is not prime, but the probability is going to be very low. That's a non-conclusive algorithm. Very recently, about 10 years ago, a conclusive algorithm was discovered, but the problem is, as the range grows larger, as you go to higher digits, larger numbers, the test becomes very complicated in terms of the required computations. So still, until today, even though the Miller-Rabin algorithm is a non-conclusive algorithm, it is still being used to test for the primality of a number in a certain range. Now, before going into the algorithm itself, and just an important thing, I don't want you to write the algorithm, or basically I'm not gonna ask you to analyze it or go through it or understand exactly every single step comes from where, but more or less I want you to know that this algorithm exists. Generally how it functions, by doing certain tests on the number using a factor of that number. If it passes the test, then you have a possibility that the number is prime. If it fails all the tests, then you are sure that the number is not prime. If it fails at least one of the tests, then you are sure that the number is not prime. And in order to increase the level of assurance, you can do the test multiple times on selected different factors of the number being tested. And if it passes every single time, then you have high probability that the number is actually prime. But you cannot be 100% conclusive still. Now, what are the basics that this algorithm are built upon? That's actually more important, and that's what we will address in this slide before describing the algorithm itself. The basic properties that this algorithm uses are the following few properties that you see here. Let's start with the first one. For any positive odd integer n, which is greater than or equal to 3, that odd integer can be expressed as the equation n minus 1 is equal to 2 to the power k multiplied by q. Now, where does this come from? I mean, logically, I'm not asking you to prove any of the theorems that we have been through, but logically, where does this come from? It's quite intuitive, right? If n is odd, right, then definitely n minus 1 is going to be an even number, right? Okay, if this is the case, and n minus 1 is even, we know that an even number can be either coming from multiplications of even times odd, or even times even, right? If you multiply an odd by an odd, you get an odd number. But if you multiply an even with an odd or an even with an even, you get an even number. Now, this is where it comes from. If your n minus 1, based on your selected n, which is odd, your n minus 1, which is an even number, comes from multiplication of evens only, then you will end up with 2 to the power k multiplied by 1, where the q is going to be 1. If it came from several evens multiplied by one or more odd number, then you will end up with some evens, which can be represented as 2 to the power k, right? Where k is just an integer with a certain value depending on the number that you are trying to test, and then eventually multiplied by some odd q, right? So the general formula here is going to be true in all cases. And let's take a test, for example. Let's take 7 as an odd number and see how we apply this to it. So 7, then if n is equal to 7, then n minus 1 is 6, and 6, we know that it is 3 times 2. This is the odd, so this is my q. This is the 2 to the power k, so the k in this case is 1, right? Let's take another example. Let's take 13. So that's n, which means that n minus 1 is equal to 12, but 12 is equal to 4 times 3. Now the 4 is 2 to the power 2 times the 3, which is my, so this is my q, and this is my k, right? And no matter how you do it, so imagine that you said here, no, it's 6 times 2, fine. You still didn't get any odd yet, so you need to get the odd value. So this is going to be 3 times 2. So you end up with 3, that's the q, and then you have 2 times 2, which is 2 to the power 2, and this is going to become your k. So you'll end up with the same result. It's a unique representation, right? So that's quite straightforward. Okay. The other property, or the other important property also, is if you select a prime number p, and then you select an integer a, which is smaller than that prime number, but it is positive, so it's greater than 0. And if you take the a to the power 2, so if you square that a, and you find it equal to 1 mod p, then one of these two conditions must be true. Either the a itself mod p, rather than the a square, is equal to 1, or the a mod p is equal to minus 1. And remember that when we do those modulo arithmetics, we try to avoid the negative. So this means that the a mod p is equal to actually p minus 1, right? That's the same as saying minus 1. Because the remainder is minus 1, which means that this number is actually 1 less than the p. So it's p minus 1, okay? Now let me try something with you. So let's take our prime, for example, equal to 7. And let's take our a equals to 6, right? Now, a squared is equal to 36. But then 36 mod P, which is mod 7, is equal to 1. Because if you divide 36 by 7, the result is equal to 5, and the remainder is 1. So that's the remainder, right? So now we know that a square mod P is equal to 1. Now let's check A. A, which is 7, which is 6, mod P, which is 7. What's the result? A is 1 less than 7, so we can say that this is minus 1. Or we can say that if you divide 6 by 7, the result is 0 and the remainder is 6, which is P minus 1, right? That's P 7, so P minus 1 is 6. And this is the same as this, by the way. These two things are equivalent to each other. So we see that in this case, the A, since the A square mod P was equal to 1, then we found that A itself mod P satisfied the second condition, which is it's equal to minus 1. Okay. The other property is a little bit more complicated, and it says that if P is greater than 2 is a prime number, and A is greater than 1 less than P minus 1, so that's an integer which is in the range greater than 1 less than P minus 1, and we notice that we can write the prime number using this formula because the prime number is always an odd number, so P minus 1 is equal to 2 to the power. Then one of the following conditions is true, right? A that we selected here, raised to the power Q, which is the odd number that comes from this representation, is going to be equal to 1 mod P. That's the first condition, or so either one of those two conditions is true. Okay, we can find some J greater than 1 less than K, where K is this, right here, it comes from this representation, such that A to the power 2J, so let's say J here is 3, so 2 to the power 3 minus 1, which is 2, so 2 to the power 2, multiplied by the Q, the odd number that comes from here, is going to be equal to minus 1 mod P. And that depends on, I mean, you need to try different J's until you get the one that allows you to get this. This is under the condition that we have P greater than 2, it's a prime number, and we have some A smaller than that prime number, then either A to the power Q is going to be equal to 1, or we can find some J that satisfies the second. Again, this is not very useful. Those two properties are quite useful to keep them in mind, but this is essential to understand the algorithm that we go through previously, that we'll go through, which is the Miller-Rabin algorithm. So the algorithm is trying to do those two tests, this one and this one. And if there is a failure in one of them, then definitely the number is not a prime. If it passes both of the tests, then the number could be a prime, the number being tested, but we are not sure. So let's see how the algorithm works. You pass a number n to be tested for primality. Let's say I want to test if 1,000,001 is a prime number. So I pass n as 1,000,001. Then I'm going to find an integer k and q with k greater than 0, q is odd, such that n minus 1 is equal to 2 to the power k multiplied by q. So I'm going to take that to 1,000,000, and then I'm going to factor out the million to 2 to the power k multiplied by q. Q is an odd value, and then the k is going to be some integer, which is 2 to the power of that multiplied by q will give me the 1,000,000, right? And then I'm going to select a random integer, a, which is between 1 and n minus 1. So it has to be smaller than n minus 1 and greater than 1. And I will start. If a raised to the power q mod n is equal to 1, then it passes. And then I'm going to try also for the j's from 0 to k minus 1, the second method. And if I satisfied, then it passes both of them. Then I'm going to say that this so either it passes this one or it passes the other one. Then I'm going to say that this might be a prime number. Otherwise, I'm going to return that it's not a prime number. So these two tests, if one of them is succeeding, then I stop there with a non-conclusive. I know that it might be a prime number. Okay, that's it. Now, this has a possibility of doing a mistake. So how do we overcome that or reduce that possibility? By again going and selecting another random a and doing the test again, and maybe repeating the test 10 times. It becomes that the possibility that it will pass the test in all the 10 times is very, while the number is not prime, becomes very low, which means that if it passes in all the 10 times, there is a high possibility that the number that I selected is actually prime. So still I am inconclusive, but the high probability of making the correct decision. Otherwise, if it fails only once in all these, fails both of them, so it doesn't come from any of them, then definitely I know that the number is not prime, and I move to the next one. So that's basically how the Miller-Rabin algorithm works. Okay. Again, I just want you to know that there is such an algorithm, that it is non-conclusive to say it's primary, it's prime number, but it is conclusive in saying it's not a prime number, that it works on two conditions. If one of them is true, then the number might be a prime number, and I don't need to test the other one. If both of them are false, then the number definitely is not a prime number. That in order to make it more accurate, you need to repeat it several times. Each time you pick a different factor so that you make sure that it passes many times with different factors, which means that the possibility that you make a mistake becomes very, very small. Why we still use this, even though it's inconclusive? Because it's very efficient computing. While recently, in 2002, there was an algorithm by those guys, which actually is very inconclusive. So it can tell you it's a prime number for sure, or it's not a prime number. But the calculations required is really very high. It's known as the AKS algorithm, and accordingly, people are still using the Miller-Rabin algorithm, even though it's inconclusive, by doing it repeatedly. Because even if you repeat it many times, it's still much more efficient than this conclusive algorithm. Okay. One of the key theorems in number theory is called the Chinese remainder theorem. And the Chinese remainder theorem, the reason for the naming is that it's believed that it has been discovered by Chinese mathematician Sun Tzu around 100 before Christ. So that's like more than 2,000 years ago. It just says that the Chinese remainder theorem, in its essence, says that when you are dealing with a number modulo high base, so mod m, and m is a large number, right? You can reduce that representation to elements. We call them tuplets. Okay, each one of them is modulo one of the factors of the m. So that's so it allows us to work on smaller modular arithmetics, and the results that we will get applies to a larger modulo arithmetic. So the formal way of writing it is if m can be factored out into factors mi, each one of them is pairwise relatively prime, so they are factors that do not have any common divisors among them, right? Then any integer which is represented in modulo capital M arithmetic can be also represented as a k-tuple, where the elements of that k-tuple, a1, a2, ak, so maybe you can think of it as a vector, where each one of those is basically the number a itself, but taken modulo each one of those factors of the m. Remember that the m has k factors, so I have k elements here. Each one of them is the factor of a, or the representation of a mod one of the factors mi. So for example, if I have a number, let's say 124, and this number is represented mod let's say 12, right? So that's my capital M. I can say that M, capital M, is equal to 12, which is equal to 3 times 4, right? So notice that these are relatively prime. They don't have any common factors among them. Okay. So M is equal to 3 times 4. That's my factoring out. Then I can say that 124 mod 12 can be represented or can be mapped to, right, A1 and A2. I have two elements because I have two factors for the M, so the k is equal to 2 in this case, right? And the first one, A1, is equal to 124 mod 3. What's 124 mod 3? What's the remainder of dividing 124 over 3 times 3? So the remainder here is going to be equal to 1. This is the A1. And the A2 is 124 divided by 4. And the A2 is going to be equal to 0, because the remainder of 124 divided by 4 is going to be equal to 0. So basically, the 124 mod 12 is equal to, or can be mapped to, two factors. The first one is 1 and the other one is 0, where this is mod 3 and this is mod 4, right? And that mapping is a bijection, which means that it's unique. If you take those two and you map them back, you always get 124. If you take the 124 and you map it, you'll always get the 1 and 0. You will never get the 1 and 0 mod 3, mod 4 for any other number other than 124 mod 12, okay? So basically, it's a 1-to-1. Remember, of course, that 124 mod 12 is actually some number smaller than 12. It should be some number smaller. So you can reduce this. But again, once you reduce it, it becomes this unique representation, okay? Now, any operations that you perform on these elements, so if you represent 124, it becomes 1 and 0, and you represent 125, and it becomes maybe 1 and 1. Then if you add those, the first elements together, you add the second elements, you will get a new representation. That when you take it back, it's exactly the same as 124 plus 125 mod 12 and so on. So it's any operations you perform on the elements is equivalent to the operation performed on the original number in its original modulo arithmetic, right? So you can imagine that this makes calculations much easier by doing that analysis and working in smaller modular arithmetics. And it's useful also for building many other theorems in number theory. The last concept is the discrete logarithm. Now, why discrete logarithms are important? Because they are actually very useful in terms of doing encryption, and we'll come to that later. So what's a discrete logarithm? Remember that the general logarithm, so here we are talking about discrete logarithms in the modular arithmetic, right? Remember that in general, the logarithm, if I say len of x is equal to b, len or log of x to the base a is equal to b, this means that a to the power b is equal to x. That's the meaning of the logarithm of x to the base a. So the b here is the power, which is when you raise a to, you get the x, right? Similarly, in discrete finite fields, which are basically the modular arithmetic domain, we call those finite fields. We can also define logarithms called discrete logarithms. And now let's start, before going for those definitions, to understand some basic concepts, and then based on them we will build the definition of the discrete logarithm. The first thing is that powers of an integer a mod n. Euler's theorem says that a to the power of phi n is equal to 1 mod n, given that a and n are relatively prime. So I can generalize this, and I can say that in general, a raised to the power m, where I replace this whole thing by some value m, which is the value of the totals, right, is equal to 1 mod n, and at least there exists one value of m that satisfies this relation. So there is some value for m that allows me to raise a to the power m and get a value of 1 mod n, given that a and n are relatively prime. Given that a and n are relatively prime. Now we define something called, so this comes from this directly. There is nothing new here. And then we define something called the order of a mod n. And the order of a mod n is the smallest value of m that satisfies this relation. We said there exists at least one value. There might be more than one value. Generally, yes. Then the smallest value that satisfies this relation is what's called the order of a mod n. Okay. The highest possible exponent to which a number can belong, mod n, is, of course, right? Because if a to the power phi n is equal to 1, then the highest possible exponent to which, so the highest possible value of m that allows this to be true is actually the phi of n. The m cannot exceed the value of the phi of n. Okay, that's also important to keep in mind. There is a proof for this, but we're not doing the proof here. Then we define something called the primitive root of n. A number a is a primitive root of n if the order of a mod n is the highest, which means it is phi of n. Remember, what's the order? It's the smallest, right? Now, if the smallest that it can be raised to is actually the phi itself, this means that that's basically, that's it. I mean, there's only one possibility here, because the smallest is the largest possible, so there's only one possible value for m, and in that case we call the a a primitive root of the n. Now the discrete um, logarithm for mod m arithmetic is defined for generally for non-prime numbers, but we put here the definition for prime number. So if p is a prime and a is a primitive root of p, which means that a to the power phi p is the order of a. So the order of a is phi p. That's when a is a primitive root of p. For any integer b and primitive root a, we can find a unique exponent I such that p is equal a to the power I mod p. And in that case, we call I the discrete logarithm. So it's written as a discrete logarithm of b to the base a is equal to I, and we also put here which modular arithmetic we are working on. So it's a p modular arithmetic, right? Now, why we are interested in this? Because calculating the discrete logarithm is very complicated mathematically, and there are some studies, but out of the scope of this work, that says how much calculations are needed for the value of p, and the larger you make the value of p, the more required in terms of calculations, and the more difficult to calculate the discrete logarithm, and that difficulty can be used to achieve good encryption methodologies. So we'll discuss that later when we discuss the relation between number theory and cryptography. Now this is just a few tables to give you numeric examples on the discrete logarithms, and last but not least, this is the summary of what we have studied across the whole last lecture and this lecture. I hope this is useful. This is first of all useful for you to start solving or finish solving your assignment, which has been delayed until end of this week, so until the end of Saturday. And also it will become more useful when we discuss later on the requirements or the relation between the number theory and the encryption or cryptography in general.